Okay, now what happens is the dragon burns up and the ashes just drop off the rod. What's that? Yeah. This is a well-known phenomenon, spontaneous combustion. Okay, so the dragon goes poof, the ashes just fall off the rod. And the question is, what does that do to the motion? So when the dragon's ashes fall off, the rod's rotation, what does it do? The rod's rotation speeds up, slows down, or stays the same. Yeah.
Before, we never actually confirmed whether or not linear or momentum was conserved.
So the angular velocity after was omega equal to omega naught over 2. The velocity of the mass afterwards would be what? Or maybe just speed. I lost whoever it was who asked the question. Yeah. What?
I don't know.
Okay, so how far is it away from the axis of rotation? D. Okay, so the speed afterwards is going to be omega times the distance from the axis of rotation. So that is omega naught over 2 times d. So what's the answer? It's not, it's cut in half.
What about the dragon?
Well, now we're on to the dragon toast. So the dragon burns up, falls off, ashes just leave the system or tumble to the ground. And what do you say? You say, I must have done something to screw this thing up. Probably it's because it's on the wrong. Let's try that. Except that I can't. No. Buzz. Okay, you guys said 74% that it speeds up, and 20% that it stays the same. Okay, why does it speed up?
You just do the same procedure like you just did, but in reverse. So L initial is we'll call that.
So he says you do the same thing in reverse. Okay, so let me try this one more time, people. So I came to rest, or I all of a sudden slowed down because I dropped the mass. What? Thanks, Professor S. So, did the mass, as I dropped it, stop going around? Did it? Well, let me say this: is it going around with a velocity like my thingy? Okay, and now watch it as I drop it. Did it all of a sudden fall straight down? No, it was still going round in the same way. Right? No. You're be puzzled.
Well, it wasn't going around, it was going tangential to where it's released.
Right. So if the definition of going around means you've got to be going exactly in a circle, then you're right. It turns out that the physics doesn't care if it's going around in a circle. This carries the same angular momentum if it's moving in a straight line tangentially. And we can derive that if you like. Let's do it. So now I want to ask, suppose that I have a mass. It was going round in a nice circle at constant angular velocity, and then I dropped it, and so it continued now to move in a straight line at constant velocity. And the question is, by the definition that we have of angular momentum, is its angular momentum preserved? So initially, L naught would be m. I'm going to call this distance r. When it's here, it's moving around at speed it has moment of inertia mr squared, and it's going at omega naught. So I'm going to need to know how fast is it going initially. What's v naught? V naught in terms of omega naught and r. Would it be just omega naught times r? Okay, so this would be omega naught times r. Now it continues up at that constant velocity, and the question is, by our definition of angular momentum, is it conserved? How the heck can I do that? Because now r is changing, right? The distance to the axis is getting bigger, right? Damn. What am I going to do? But the amount that it's going around, that doesn't seem fair. If it's going up, that's not going around. There's only a component of the velocity that's going around, right? It's going to be that component of the velocity that corresponds to going around, right? So, well, let's think of it this way. We want to calculate omega, which is d theta dt. And this side will be, well, let's see. If time 0 is here, then this length would be what in terms of time? V naught times t. So let's see, the tangent of theta should be what? V naught t over r. So let me differentiate both sides with respect to t. What's the derivative of tangent? Secant squared, but I have to use the chain rule, right? So this is secant squared theta times d theta dt is equal to v naught over r. Do you agree with that? What's secant squared? That's like 1 over cosine squared. So I wanted to know what this was. So d theta dt would be, hey, wait a second. What's v naught over r? That's omega naught. So omega naught times the cosine squared of the angle theta. Agreed? If I just multiply both sides here by cosine squared, that's what I get. Okay, now, what's the moment of inertia? Well, now it's farther away, so I is equal to m little r squared But little r times the cosine of theta is what? Big R. So L final is equal to I omega, which is equal to m r cosine, doofus, don't do that. M little r squared d theta dt, which is equal to m big R over cosine theta squared times omega naught cosine squared theta. Because this part is d theta dt, and this part is I. So the cosine squareds go out, and I'm left with m r squared omega naught. So what's the conclusion? It is the same. So even though something is moving in a straight line, doesn't imply that it doesn't have, well, that's a lot of negatives, does not imply that it is devoid of angular momentum. Okay? So when the dragon falls off, the ashes are still moving. They carry away the angular momentum of the dragon, and the rod persists with its angular momentum. There's no external force that's changing the angular momentum of the rod. Any question on that? So there's subtle, definitely subtle things going on here.